I'm a PhD student at Keele University. As Vincenzo introduced nicely, I'm studying galaxy clusters behind the Magellanic Clouds using the VMC survey. So, yeah, why would we want to study galaxy clusters at all, and why would we do it behind the Magellanic Clouds of all places? So galaxy clusters are important sort of labs, if you like, for studying galaxy evolution as places where there are loads of different interactions between galaxies going on all the time. And the Magellanic Clouds are actually very well covered by lots of different multi-wavelength surveys. But in terms of studying galaxies, the area of sky behind them is a lot less well studied than the less obscured areas of the sky because of the Magellanic Clouds and all of the stars and the dust that is in the way. I don't really need this slide because you just had Vincenzo's talk, but the important part about the VMC survey and why it makes it possible to study galaxies behind the Magellanic Clouds is it's the highest resolution of near-infrared survey in this part of the sky. So it allows us to see galaxies actually through the gaps between stars, and also it's high sensitivity, so it allows us to see further back than we've ever been able to see before in this part of the sky. This is an example of just how we can see the galaxies between the stars. So this is what I'd call the worst case scenario. It's actually right in the middle of the SMC. So other areas actually look better than this for seeing galaxies. And I've just sort of highlighted a few examples of galaxies. I know that's not all of them. Of course, all of these galaxies have all the dust in front of them, so that causes them to be reddened, and also a lot of extinction. For the reddening, we can account for that, and I do so by using the gas gap H1 survey. That's a high angular resolution radio survey of the H1 gas that covers the Magellanic Clouds and also the Milky Way area in front of them. I'm able to do this because H1 works as a tracer of dust, and it's high resolution enough that I'm able to give every galaxy sort of its own reddening. Is just a plot to sort of demonstrate that. So this is everything, not just the galaxies. I know it includes stars. You can sort of see the imprint of the SMC on this. But everything generally is sort of moved up and to the right by the dereddening, but not by the same amount. Because everything everything, and even actually pretty much every source gets its own reddening. So as well as the reddening, of course, then I have to deal with the stars that are in the way. Probably one of the biggest problems is separating the stars and the galaxies in the data. So yeah, one way I'm doing that is just basing it on proper motions from Gaia. So yeah, in theory, galaxies ought to have sort of a zero proper motion, and the Magellanic Clouds and the Milky Way ought to have some proper motion. In practice, this probably works a lot better for the Milky Way than for the Magellanic Clouds, but it makes it possible for us to sort of tell the most obvious things, most obvious stars apart from the galaxies. What I'm doing with this is using a sort of what I'd call a training set of what I think would be Magellanic Cloud stars based on a color magnitude cut that I've done based on this diagram from El Yusufi et al. And yeah, this is sort of making like a safe sort of set of things that I think should almost certainly be Magellanic stars. And then I'm sort of propagating that out to the rest of the sources, and trying to make, trying to tell the stars apart from the galaxies. These are the results. These are some of the results of that so far. Just taking like a slice through the SMC. You can see it sort of works a bit better for the foreground, as I said, than it does for the Magellanic Clouds. But it allows us to filter out things like 47 Tucanae that's in the on the right of the top left diagram, and yeah, it works. It doesn't filter out everything, but it works for the most obvious things. Yeah, the main thing, the main next step to tell to separate the galaxies sort of into the clusters is we want to work out the photometric redshifts for every galaxy. So I'm doing this with machine learning methods. One of the methods I've tried to use is random forest regression. I've tried this based on a couple of training sets. So I can train it on Ultra VISTA and the SDSS together with the VIMOS Ultra Deep Survey. But yeah, for this will only work so far just for the VMC because of the VIMOS Ultra Deep Survey that I haven't added an optical counterpart to. But the other training set, which is Viking, 3D HST, and the Dark Energy Survey, is can be used for the VMC and also the SMASH survey, which is a DCAM survey of the Magellanic Clouds, so that adds the optical element to it. These are just some of my, I suppose I'd call them preliminary results. This is sort of how that comes out after a color magnitude cut when using the Ultra VISTA and SDSS VUDS training set. I don't believe that this long tail to the right is actually real. I think that we probably can't see anything above about redshift 2. I expect those are outliers. But it shows the sort of distribution that it shows a sort of distribution of redshifts where there are more galaxies in some areas than others. But I don't really trust it, and I think it might be overfitting because when I change the training set, then the distribution sort of changes quite a lot. When I change the training set and add in SMASH, that is the distribution. Yeah, distribution changes quite a lot. Another method that I've tried is using Bayesian regression instead. This adds in the element of having an uncertainty, which I think is quite important for something like a photometric redshift, especially if you're trying to find galaxy clusters. So this is just sort of early results of what happened with that when I split up the training set and sort of tried running it against another part of the training set to just the comparison of the true value and the predicted value. It doesn't work so well on sort of higher redshifts. I think maybe because there's less examples of that in the training set, but and it classifies some things as having a redshift of less than 0, but I think those might be stars. So perhaps that doesn't matter. But when I run it on the actual test data, this is only for things that are classified as galaxies in the SDSS, but it seems to sort of cut off at about 1 and produces this Gaussian effect, which might be something to do with the observations themselves. And yeah, not totally sure, but as I said, these are quite early results. I'm also doing some case studies for the nearby, for sort of the nearby clusters. So there are sort of 2 large structures that we know about. We can see them in the you can see them in the 6DF galaxy survey and other things. And so yeah, we can already start studying these. The top left is an example of a wide angle, narrow angle tail radio source galaxy from one of my colleagues. We called it the mouse because it kind of looks like a mouse, and that we think is part of a cluster. So for these sources, we're taking spectra with the Southern African Large Telescope to try and determine sort of the membership, cluster membership for these, and also to study the kinematics, sort of to see what's behind these interesting. If we find interesting radio phenomena with EMU, for example, then yeah, we want to look further into that by taking spectra. Also, yeah, the sort of cheat one, as I call it, because the Abell S0362 cluster happens to be in one of the Magellanic stream tiles of the VMC, so it's not really in an obscured area, and we can kind of just study that one without worrying too much. But it also makes for a good sort of comparison for the other parts, to have a cluster that's in our survey that isn't obscured. So the next steps for this are sort of, well, actually deciding what is a cluster and what's just sort of a bunch of co-located galaxies. So yeah, and then we're planning to make a catalog of the clusters once we know, once we have the clusters, and to publish that catalog. Yeah, these methods could be adapted potentially to other parts of the sky, especially other sort of obscured parts of the sky. They might be potentially useful in the galactic plane, for example. So yeah, in summary, we're finding galaxies that have previously not been identified in the. We're finding those in the VMC images. We're using those to try to find galaxy clusters, and yeah, we're planning to publish a catalog of that. So yeah, thank you for listening. Thanks to all of my collaborators, and those are references.